Now it worked. It's weird. I've had that before where
Yeah.
it works and it doesn't work. All right. So amateur radio operation is basically transmitting information by generating radio waves and applying some form of modulation to those to impart the information to it. We call the radio waves electromagnetic because it's composed of an electric field and a magnetic field. And you can see in that diagram, the red is indicating the electric field or electrostatic field, and the blue is representing the magnetic field. And they're at right angles to one another. We call one the E field, which is the electric field, and the magnetic field is the H field. Probably because of Henry. I'm not sure why they picked H. And you see there in the bottom right, it's showing the propagation direction. So you have that E field, which in this case is horizontal, and it's moving in the propagation direction. So it's moving horizontally. In the real world, you actually rotate that thing around. So it's a three-dimensional object, not flat like that. But in this case, the electric field, regardless of whether it's this, horizontal, vertical, like in the diagram, it's moving in the horizontal direction. So relative to the Earth, it would be moving horizontally. If we rotated that 90 degrees, then it would be vertical. The reason I bring that up, and we'll talk about polarization in a little bit, and that's what polarization is the position of the electric field in relation to the Earth. So what are two components of a radio wave?
Charlie, electric and magnetic fields.
What's the relationship between the electric and magnetic fields of an electromagnetic wave?
I was going to say
Delta?
Charlie.
Well, let's go with delta. They're right angles. They're the big word is they're orthogonal.
$50 word for today.
You could also say they're in quadrature. Another big word.
Yeah.
Okay, so they have characteristics which we need to know about. One is frequency, which is how many times per second that wave I guess replicates itself. So in most cases, we're talking about a sine wave or some combination of sine waves to make different shapes, but they're all basically sine waves. So one complete cycle of that sine wave is how we measure frequency. So how many times it cycles back and forth per second is what we call the frequency, and we measure that in hertz. And we learned about that last week, a capital H, small z to represent hertz. It has kind of the reciprocal of that, which is wavelength, which is the distance that the wave travels in one cycle. And assuming that it's traveling at the speed of light, which it would in free space, we can calculate what the wavelength is by knowing the speed of light and dividing the speed of light by the frequency, which is how many cycles per second there are, which will tell us how long each cycle is in, and normally we do that in meters because we typically use the speed of light in meters, which is approximately 300 million meters per second. It's actually 299 something, but 300 million is close enough. We use this letter C, normally the small letter C, and I think I got a capital there, to represent the speed of light. You might be familiar with it in Einstein's E equals mc squared. It's the same C. And like I said, these waves will travel at the speed of light if they're in free space, not being affected by anything and no what we call dielectric. When we generate a radio wave in a conductor, it's going to travel at a slower speed than the speed of light, depending on the dielectric around the conductor and the size of it, and that will give us what we call the velocity factor, which is the ratio of how fast it travels versus the speed of light. So I'm getting ahead a little bit, but you'll need to know it at some point. So and this chart just shows the entire spectrum and where radio waves actually are, and you see it's basically down there at the bottom. And then above radio waves, we get into the infrared, get into the visible light spectrum, and then up into the ultraviolet, X-rays, gamma rays. And you can see that the wavelength increases the lower the frequency. The higher the frequency, the wavelength gets smaller, where they get down into the fractions of a nanometer, and the energy increases. So it takes more energy to generate a higher frequency wave. And the one thing not on this chart is when you get up to from basically DC up to light, we call that non-ionizing radiation. When you go from light on up into the ultraviolet X-rays, that's ionizing radiation. And the difference is ionizing radiation can damage cell structure, screw up your DNA, and eventually with enough X-rays, gamma rays kill you. The non-ionizing, when you get in the infrared, will cause severe burns, but it won't necessarily kill you. And we'll talk about that when we do the safety part. We talked about the wavelength, which is the distance that the wave travels, in this case, from one peak to the next peak. It could be from a trough to a trough or where it crosses zero, but it's a complete wave, and how far it travels in time based on its velocity, which is something the speed of light or less, depending on the medium. So the way we calculate it, and we use the Greek symbol lambda to represent wavelength. So we say lambda is equal to the speed of light divided by the frequency in hertz, and that will give us the wavelength in meters. Now, since people tend to be lazy and they don't like writing all those zeros, so instead of writing 300 million divided by F, if we divide both F and C by 10 to the 6th, we can reduce the formula to 300 divided by the frequency in megahertz. So if we use megahertz, we only have to use 300. So it gets it down to where you can basically do it in your head without a calculator. And again, the lower the frequency, the longer the wavelength, the higher the frequency, the shorter the wavelength. Those are the key things to remember because those are the test questions. There's a couple examples there where 7.15 is a typical frequency in the middle of the 40-meter band, and we'll talk about the difference between bands and frequency in a little bit. And it comes out, if you calculate it, to 41.95 meters. So we do the band representation as an approximation. So it's approximately 40 meters. The one that's kind of covered up is a 20-meter one, the 15 megahertz, which is actually a little bit above.
It's easier to say 40 meters than it is to say 41.95 meters.
Right. We tend to be lazy. So what is the velocity of a radio wave traveling through free space? Got a guess?
Charlie.
Charlie, read the question carefully.
Alpha.
Alpha. That's the one key thing on the exam. Make sure you read the question carefully. In fact, read it twice and read all of the answers before you answer. What is the approximate velocity of a radio wave in free space? Is it Bravo or Charlie? Bravo, 300 million meters per second. Now you can actually change that formula to do feet, but it changes the number. It's 498.
I was thinking 768. What I was thinking.
Yeah, forgot. Don't use that one much. What is the formula for converting frequency to approximate wavelength in meters?
We were both way off.
I think 468 gives you halfway in feet.
That would be it. It's coming up 984.
Okay.
Formula for converting
Delta?
frequency to approximate wavelength in meters.
300 divided by the frequency in megahertz. That sounds pretty good to me. So you can see in the formula there, instead of having to write out 300 times 10 to the 6th divided by a frequency times 10 to the 6th, you just shorten it to 300 divided by the frequency in megahertz.
Right, because top and bottom of 10 to the 6 cancel out.
Right. And actually, I got a mistake there that F shouldn't be sub megahertz, it should be hertz times 10 to the 6.
Oh, yeah.
I didn't catch that one before. What is the relationship between wavelength and frequency? I've mentioned this several times.
Beta. Bravo. Wavelength gets shorter as frequency increases.
Right. Okay. So we define radio frequency basically as any radio frequency in any mode. When we say RF, it's just kind of a generic term. And we refer to frequency and wavelength both kind of interchangeably. You'll learn what bands, which we define in wavelengths, are what frequencies. So it's easier to talk about the 20-meter band or the 40-meter band or the 70-centimeter band than it is to talk about a specific frequency, because the band represents a group of frequencies. Like, for instance, the 2-meter amateur band, which you'll be able to use as a technician, goes from 144 to 148 megahertz. We call that the 2-meter amateur band. Actually, if you work it out, it's slightly longer than 2 meters. So 148 megahertz comes out to 2.03 meters. 144 would be even longer, but they're in approximately the 2-meter wavelength range. The normal range of frequencies that amateurs use are kind of divided up into some sub ranges we call medium frequency, high frequency, VHF and UHF, very high and ultra high. And we normally just say HF or VHF or UHF. I believe I sent everybody a PDF of this, which is the technician band chart, which shows that the bands technicians are allowed to operate on and what frequencies and modes. And you'll see down there at the bottom, you can do CW on the 80, 40, and 15-meter bands. And you can do voice on part of the 10-meter band. And then in the VHF, UHF range, you basically have full privileges. This is showing the frequencies associated, and you see they go up by powers of 10. So the medium frequency, which would be the 160-meter band, and I guess AM radio is also in that.
Yeah.
Isn't used too much by amateurs, although I guess more people are starting to play with 160. The problem is it takes a very long antenna. The HF band is from 3 megahertz to 30 megahertz, and that's an important one to remember, 3 to 30. VHF starts at 30 and goes to 300 megahertz. So the 2-meter band is in the middle of the VHF frequency subband, whatever they call it. And then UHF goes from 300 to 3000 or 3 gigahertz. And that's where the 70 centimeter band, which you can use, is. There's also a 1.5 meter, which isn't used much, and a 23 centimeter. And then you get up into the gigahertz stuff, where there are some people that play with that nowadays. In addition to frequency, which of the following is used to identify amateur radio bands? Alpha. The approximate wavelength in meters. And I listed them down there, all the ones that you can operate in. There's some restrictions on what they call the warp bands, and I forgot what that stands for. It's WARC, where in some contests you're not allowed to operate on those.
World.
Yeah, World Amateur Radio Consortium or something. They're shared bands, which is why. What frequency range is referred to as HF?
Bravo.
You sure?
UHF is definitely alpha.
That's correct. So VHF would be what?
Oh, VHF would be Bravo. Then C is HF.
Okay.
Charlie.
What frequency range is referred to as VHF? You just did it.
Bravo.
Very good. What frequency range is referred to as UHF?
Delta.
Didn't expect that one, did you? What does the abbreviation RF mean?
Alpha.
Okay, so we learned about radio waves consist of an electric and a magnetic field that are orthogonal or at right angles to one another. The speed of light is approximately 300 million meters per second. The formula for wavelength using lambda in meters is 300 divided by the frequency in megahertz. That wavelength decreases as frequency increases, and vice versa. It increases as frequency decreases. Amateur radio bands, the HF is 3 to 30 megahertz, VHF is 30 to 300, and UHF is 300 to 3,000 megahertz. And RF refers to any frequency or mode.